Perfect. And we're live streaming as well. So good morning or good evening to wherever you are. Excited to see you here today for the Womanium Quantum Computing Entrepreneurship Program. We have two amazing speakers for you today. Malu?
Yes, we will start with The Quantum Ecosystem Needs You by CELIA MERZBACHER. Very exciting talk. How do we get quantum innovation? What does the quantum workforce need? What is the quantum ecosystem like, involving all companies, national labs, universities in the US and beyond in the world? And then we will dive deeper into the physics and how to implement quantum computers with Caroline Figuette from Quantinuum about TrappedIon quantum computing. Prachi will introduce our first great speaker, CELIA.
Yes. So Dr. CELIA, she is the Executive Director for the Quantum Economic Development Consortium, QED-C, as the name says. And QED-C is a consortium of over 200 partners from industry, labs, academia, and government. So she knows everything that's happening in the quantum ecosystem through the US. Of course,
it looks to me that the internet connection is bad. So please start bringing up your slides, CELIA.
Okay.
Executive Director of the Quantum Economic Development
Policies for the country.
Oh, and Prachi, you are back. You were briefly cut. Could you restart your introduction?
Absolutely. So excited to introduce you to your Dr. CELIA today. Dr. CELIA is the Executive Director for QED-C, which is the Quantum Economic Development Consortium. It's a consortium of over 200 labs, academia, government, as well as industry. So she knows that there's one person who knows everything that's happening in the quantum world. It's Dr. CELIA. Before this role, she's been involved in a number of innovation and partnership roles, where she also used to lead and be part of the White House OSTP, which is the Office of Science and Technology Policy. And previously, she also served as the Executive Director for PCAST, which is the President's Council of Advisors on Science and Technology. So, Dr. CELIA, very excited to have you here come and speak and tell us what does the quantum ecosystem look like today and how can we all be a part of it? Thank you.
Thank you, Prachi, and thanks to everyone who's put together this fantastic course. Really, the people who are participating are getting a great introduction to this exciting field of quantum information science and technology, or sometimes we just call it quantum for shorthand. I want to just remind everyone that quantum is more than just quantum computing. That's an important and particularly interesting application of quantum physics and quantum properties of matter. But I think you're going to hear more tomorrow about quantum networking and communications and sensing. So there's a huge diversity of applications that are going to develop over time. And there are many, many opportunities in this emerging industry that I'll talk to you about today. So my message at the end is really that this is such an enormous and impactful area that it really needs many, many people with many different kinds of expertise and experience. So I hope by the end I'll have you convinced that you're on a good track and able to contribute and participate in this growing field. So what I will cover today, very briefly and quickly, are the following, and this is what you'll sort of learn, I hope. What is the quantum ecosystem? It is broad, inclusive, and because it's early stage, it really includes all parts of what you might think of as the innovation ecosystem or community. How is innovation happening? A lot of you may be thinking that you've got ideas that might be something that could be eventually developed into something practical and useful. And I think that's fantastic. My opinion, having worked in a lot of different fields over time, is that the really exciting innovation happens in small, nimble organizations, startups run by people who have a vision. So I'll talk a little bit about how quantum innovation is happening. And then I'll also touch on the workforce needs and the opportunities in that space. So the quantum, and I said quantum computing here, but really it should just be quantum innovation ecosystem, includes all of these different what I call actors or players. And I sort of have abbreviated them in this slide, so I'll just run through them very quickly. At the top, we have academic or institutions, universities and colleges. That's where a lot of research and education happens, of course. Then we have industry. Industry does a lot of research, invests in typically research that's needed to lead ultimately to products. So it's typically more applied research than what takes place at universities. And then I have this third category at the top, research institutes. I happen to work for one of those. I work for SRI, which is Stanford Research Institute. It's a not-for-profit organization that does mostly government funded, but sometimes also industry funded research to take things from the very earliest stages, often the sort of stage that they're at universities, and bring them a little farther along so that industry can take the risk and make the investments to actually manufacture and produce the technology. So getting prototypes done and more applied research typically. Then in the middle, we have government, and that's government around the world, invests in a lot of early stage research, but also more and more is interested in getting the results of those early stage investments out into commercial use and get the economic benefit of making a lot of investments in university and other discovery type of research. So government has multiple roles to play. They also are, in some areas, a customer of technology. So they may need new AI-based IT systems for being able to analyze data and do their various missions. Each part of the government has a different mission. So the government is both a developer and a customer of new technologies. Then I put in a separate category the national labs, and these are government-funded laboratories where, again, they're addressing the needs of a particular agency in the government. Here in the United States, we have a number of national labs that are funded by our Department of Energy, and they naturally have an energy focus, although that's very broadly interpreted, and they do quite a lot of very basic research. They also are the home in the US for the high performance supercomputing technologies. And so those labs are where a lot of the very advanced computing expertise resides, and they'll have that role of working closely with industry and the academics to advance technologies for their missions. At the bottom, I include investors, VCs, venture capitalists, also private equity and other forms of investment that would be outside of the company itself. So for us, an entrepreneur or a startup, they may be looking for investors, and that community is going to be really important. And they need to understand what this technology is about. So there's a sort of need to educate and make sure that they see this as an emerging field that's going to lead to significant economic value in the longer term. We have educators outside of universities that are critical. So there are certainly community colleges or technical colleges that are training technician level workers that are going to be really important, as well as even earlier than college, what we call the K-12 or the high school and younger learners. So educators of all kinds are part of this system. And then the last one that I show on this chart is standards developers. And that's a sort of less visible and maybe not the first group that you think of when you think of new technologies. But if you imagine, in order for your monitor to plug into your computer, in order for your phone to plug into the charger, in order for all of these technologies to work together, you need to have standards in order to sort of have everybody on the same page with certain technologies. And it's early to create the kinds of standards that allow for things to connect together, because we're still figuring out what kind of technology is going to ultimately be the one that becomes commercial in some cases. However, we need to be starting already now to bring the communities together to talk about what I call sort of the specifications, so that we all agree on how we're describing the components that go into a quantum system. What kind of electronics do we need? What kind of lasers? What kind of optical components? These all need to be understood, described, and sort of standardized, at least in terms of the way we talk about them as a research community, R&D and innovation community. Okay, I'll move a little more quickly through the rest of the talk, but I wanted to give you a good sense of all these different players that are involved. Now, for a quantum system to be built, there's a whole supply chain that goes into that. And it's another way of organizing the quantum universe. So here I've put at the top what I call the end users. These are the companies that need quantum technology to improve their business, to grow their company, to do a better job, or to save money. And I just show some of the different kinds of industries that are going to benefit from quantum, and quantum computing in particular, perhaps. So I see I have sort of a typo. I put them on 2 lines. Pharmaceutical companies, banks, and other financial institutions, they are heavy users of computing technology. For instance, if a bank wants to figure out what the most profitable portfolio of investments are for their shareholders or their clients, they could use quantum computers to do a better job than they can do with a classical computer, possibly. We're still at the stage now where we're developing the quantum computers that are powerful enough to do these calculations. And also, we have to develop the software, because you can't just take the programs that run on a classical computer and port them or migrate them to a quantum computer. A quantum computer really runs completely differently. And so there's a huge field of what I call quantum computer science, about developing the new algorithms to run on quantum computers to do the kinds of problems that companies like these care about. Pharmaceutical companies are trying to search through thousands and thousands of possible drugs to figure out which one is the best. And a quantum computer could help with that. Automotive companies who are doing driverless car development and want to be able to, again, do machine learning and be able to safely navigate could benefit from quantum computing, and many more. So there's a huge number of end users in the supply chain. So who's going to send the technology and make the products that the end users need and want? Well, that's where the system developers come in. And those are the Quantinuums of the world. We're going to hear from Carolyn later. IBM, Google, and some pure play companies that are all about quantum, like Quantinuum, IonQ, Rigetti. These are all companies that are developing the hardware systems. There also are companies that are focused more on the software that's going to be needed. And then there are companies that are really in between the users and the developers, cloud service providers. And already today, you can access some quantum computers via Amazon and Microsoft. And so these are all part of the sort of system level development that's going to interface with those end users. Then for the system developers, they've got to buy components to put into their system. And you can see some of those spelled out here. Depends on the type of quantum computer. You may need something that's going to focus light and manipulate light and photons. You may need something that keeps the system ultra cold, near absolute zero, and so on. And so there's many, many suppliers, and those are companies that make lasers, that make electronic components, et cetera. They don't have quantum in their name. And they're having to learn about this new field and develop new products and serve new customers with those products. And then at the bottom are really the people who make materials, do fabrication development, the really fundamental capabilities that are going to go into making the components that go into the systems. So I wanted to touch briefly on an idea that you may have heard about called technology readiness. And there is a scale, the technology readiness level scale here goes from 0, which is just things that are sort of in the idea stage, through 9, and that's a fully commercial manufactured item. And in between, you have progressively more advanced technology readiness as something goes from that idea stage to a practical application and a commercial product. And usually there are different of the actors in the innovation ecosystem that are working at different parts of this technology readiness scale. So typically universities are doing the basic research that's at technology readiness 1 or 2, but then very quickly they publish a paper and move on to the next research thing. And so then it has to be handed off to someone who does more applied research, maybe one of those research institutes like SRI or a national lab, or maybe a company that has venture capital funding to take something that's just at that earliest stage and bring it forward and get rid of the sort of technology hurdles that are in the way. Ultimately, it has to be invested in by somebody who's going to make it and sell it. And that's typically a company. And so there's a whole sequence of players that are involved with moving something across these technology readiness levels. And here I sort of take that idea. So you can see technology readiness level is now shown on the x-axis. It's increasing as you go from left to right. And then on the y-axis is shown investment levels, and different parts of the ecosystem are playing in these different technology readiness levels. So it's just showing the same kind of idea in a different way here. So again, at the low technology readiness level on the left, you typically have government investing and universities doing the R&D. And then you have the private sector, both investors and companies making big investments in the highest technology readiness level, but there is a gap in between often, and it's sometimes referred to as the valley of death. And at the bottom, the sort of steps along the way are also shown. This is from a Government Accountability Office report, GAO report, that you can find on the internet. So there are programs that fill that gap. And just one that I put here is the US government seed investment program called SBIR. It has another sort of cousin called STTR, and I spell them out down below: the Small Business Innovation Research Program and the Small Business Technology Transition Program that helps move things from universities out into applications. So other countries have similar funds that they use to make these kinds of investments, but it's a recognized gap that needs to be filled somehow. And quantum certainly is a technology that's emerging, and we need to think about how to fill the quantum gap. I'd like to transition now to spend the last couple minutes talking about the workforce needs. I know many in the audience are at early parts of their career or still maybe in school. And so I wanted to share with you some information that my organization, the QED-C, has developed by doing some surveys. So in 2020, 2 years ago, we surveyed the industry members of the consortium to ask them 3 questions. The first question was, what jobs do you think you're going to be trying to fill in the next 3 to 5 years? And we had a big list that they could choose from, or they could write in an answer. And that list that we gave them, the menu that we gave them, was based on an analysis that we did of job postings. So we tried to identify what we saw as the jobs that the companies were trying to fill today. So once they clicked on a job and said, well, I'm going to be hiring quantum algorithm developers, then we would ask 2 follow-on questions. One was, okay, what skills do you want those people to have? So we had another big menu. They could check anything on that menu they wanted to that would go with that job, or write in additional skills. And the last question was, and what degree do you think, what education do you think those people that you want to hire should have? What would be your preference? So we had a very rich set of answers on the types of jobs and work roles and the skills and education that companies anticipated needing. And this is just the analysis of the part about degrees, and in particular, the level of the degrees. But you can see this archive link down here, and there's a paper that you can easily find that was published based on this survey, and you can read all of the results. The sort of takeaway messages that I want to leave with you are the following. Number one, there are a lot of different types of jobs, and you can see the names of the jobs that are shown on the list here on the left. And those jobs, many of them do not have quantum in the title. So there's data scientist, there's photonic engineer. These are all jobs that you may be thinking you were going to, work toward, and now you're interested in adding quantum to it. And that's completely doable. You don't need to go back and get a quantum science or quantum physics or quantum engineering degree. You need to get a little bit of quantum know-how so that you can add to your subject matter expertise in data science, in computer science, in photonic engineering, and so on. And this program is an example of that. So this is exactly what the industry needs, is people with deep subject matter expertise in a certain discipline, and then enough to be able to work and talk with the quantum experts in the organization. And most in this chart particularly is about the degree level. People, I think, sometimes think that this is a field that requires a PhD, and the answer is it does not. Some jobs do, and in this, the color code for PhD is green. So at the bottom, you see the ones called error correction scientist or computational chemist. A PhD is, in fact, the preferred degree. However, as you go up, you see more and more red, which means a master's degree is preferred, or purple, which means a bachelor's degree is the preferred degree. And if you add bachelor's and master's, you see most jobs require, or the preference is for someone with one of those degrees. So that's really an important message for the students to take away. And I hope that this has been helpful. So going back to the ecosystem, my organization, QED-C, is a consortium of all these different stakeholders. So I'll just take a moment to talk about QED-C, and this chart is sort of a standard chart, but what I wanted to focus on is that we look at workforce and we study the needs of the industry, as I just described. We also look at technology gaps, and I mentioned standards at the beginning. We work in that area as well. So we cover really all of the bottlenecks that stand in the way of quantum becoming a real industry. So our mission is to enable and grow the industry, and we do that with various activities and programs by bringing together all of the experts from our members. So I just want to leave behind that you can go to quantumconsortium.org. That's our website. On the top, I circled, there's a menu item that says quantum jobs. You can go there and see all the different jobs at QED-C member companies and organizations. And down at the bottom, I mentioned that we have a new program called the Quantum Office Hours Program, which is aimed at giving students access to people in the industry who can answer questions about careers in this industry. So these are all the kinds of programs that QED-C is launching. And you can follow us on Twitter, on LinkedIn, on YouTube. We have a channel. There's a lot of information out there in the public sector or public space. And finally, if you go to our homepage, there's a button you can click on to say, I want to receive the newsletter. And every 2 weeks, we send out a newsletter, and anybody can get that. There's no cost. You don't have to join. You can sign up for the newsletter. So with that, I will thank you again, Prachi. It's a pleasure to be speaking to this community, and we're all about communities, I think. So I'm happy to answer questions if there are any, or you can follow up with me via email.
Email as well. I think students are already excited. I will let them know. Chris Bishop is amazing. He will be speaking at a later session on career fairs and career panels as well. So thanks for this Saturday. Perfect. Thank you. So Celia, you've shown us some really interesting things. I think a few things that stand out are the technology readiness levels. And then the other thing is the chart itself, and students are really impressed with the chart of what are the skills that needed at what level so that you can enter the industry. Do you have some more feedback or something else you'd like to elaborate on that chart, especially as, one student pointed out that it's Louis from Carnegie Mellon, that quantum computing itself, the word quantum is very intimidating. So how do we motivate more students and more people to enter the quantum field? What have you seen that works, that doesn't work? Yeah.
I think that there are many sort of freely available resources these days. So just a little bit of searching will lead you to some very interesting material, and you can find something that's sort of at the right level for you. If you're just quantum curious, there are things that are very sort of non-math based and easy to follow and get sort of dip your toe in the water. And then if you're at CMU and thinking about science and technology and very advanced in a way, then there's all kinds of courses. MIT has a online course that's outstanding. The University of Chicago in the US also has a program that they're putting out that I think has sort of micro certificates, for instance. Those might be more appropriate for people maybe later in their education who just want to be able to say, check, I can demonstrate to a employer that I have some credentials. So also there are many professional organizations, and some students may be a member of those, the American Physical Society, Optica, and others, who are putting together boot camps and information. So I think there's a lot of different resources that are available for all sorts of different levels.
Fantastic. That's really exciting to hear. And one thing you mentioned is being able to demonstrate to future employers that I have an understanding of quantum computing and that I'm capable of working in the field. According to you, what is the best way to demonstrate these capabilities? And, is it a certificate? Is it actually working in the field as well, showing some real projects? What do you think has worked for students?
I think that, well, certainly having some courses that some universities now offer that are a sort of Quantum 101 or some intro. If you're just graduating and you can have someone write you a recommendation letter or something who says, I taught this student, they were in my class, we covered this material. I think that kind of documentation, right? You don't have to believe me, this applicant. My professor can vouch that this material was covered. It's a little bit kind of the Wild West, as we say in the US, because there aren't standardized curricula at this time. So I think you have to be a little bit creative in that regard. But again, there are these online resources that I think are being recognized, and they offer, if you pass some test at the end, they would give you some documentation of that. So I think you have to be a little bit creative and count on your mentors. I will just say to all the students out there, as someone who, is contacted on occasion to help young learners and students who are trying to make career decisions and so on, people like me want to help. So when you're reaching out, you should be as specific as possible about what it is that you need, and we'll try to help you. So that's something that I think sometimes you feel a little nervous about contacting someone who's senior or who you don't know. But whenever someone reaches out to me, hey, I was in that position myself at one time. And so be very clear about what you're trying to do, and you'll find people very interested in helping you.
Fantastic. That's really good feedback. And that's what we've tried to do with this program itself, is expose students and excite them about what's at the cutting edge, how is quantum computing also getting applied in different industries. So you've had CEOs come in from the pharmaceutical industry. Soon we'll have folks from the energy side as well come and speak. So how is quantum applied? And then get into the specifics of, well, how do you go about learning about it? What are the fundamentals? And how do you program a quantum computer, for example?
And I was on a panel once, and it was sort of a light bulb went off for me, because on the panel were some people from the quantum, let's call them the makers, the system developers, the companies like Quantinuum and others who are developing the technology. And there were people there from the end users. And I kind of came away with an understanding that the number of jobs that are going to be in the end user side of things, it will eventually far outnumber the number of jobs in the makers. When you think about it, when you just think about use of IT by all the industries in the world,
right,
every company has to have IT experts.
yes.
Only a few companies make the IT systems, but everyone uses it. And so over time, the jobs are going to more and more be with those end users. And they need people who, again, can bridge between their world, energy, drugs, pharmaceuticals, right, transportation, and the quantum world. So having that multidisciplinary kind of background is extremely valuable.
Perfect. And we're encouraging students to also solve multidisciplinary problems. It's not only about having the knowledge, but then applying it to different problems. So that's what our 1 month hackathon in August is going to be about, which is we've gotten challenges from Deloitte, we've have challenges from IBM, and about 6 to 7 other companies of real world problems where quantum computing is getting applied. So excited to see that. One other question that a student, Demi from Austin has, and the question is, what are the standards you're seeing today? And what are the challenges in developing these standards? And how do you, and yeah, I would ask the question, I'm involved in standard making as well from the automotive side. And sometimes it's really hard to herd cats. These companies don't want to work together. They're super competitive, especially at this young stage. So how do you also then handle competitiveness as well as standardization?
So I mentioned that standards are kind of come along at a certain point in the technology readiness series. And I'm actually working with some people at the National Institute of Standards and Technology in the government on a concept that explains something like technology readiness levels, but we're calling it standards readiness levels. So when is a technology ready to be standardized? And it's too early. And so what you're seeing when there's this competition and unwillingness to land on standards, that means it's probably too early. So you have to, on the other hand, standards setting and standards development is a pretty slow process because it's very consensus based. You do need all of the parties to come together and agree. And that takes time, especially if it's at the international level. Then you've got sort of geographic issues, you have to go to meetings around the world, and it just is a very time-consuming process. So what can we do now that will set the stage? I would say one of the things, and this is something that QEDC is very much working on, is benchmarking. So you somehow have to be able to determine when something is ready to be standardized. And the way to do that is by benchmarking progress. And so being able to benchmark what quantum computers can do today and watch that as it improves over time is an example of a sort of pre-standard activity that's happening. And in fact, there's a company down in Austin, Texas called StrangeWorks, great name, with some people who are really thought leaders in this area about how you measure progress of quantum computing. So there are a number of organizations that are helping to come up with ways to measure progress that are application-based, so performance-based. It's not about how many qubits are under the hood or how low the temperature is. That's important. The system developers have to track all of that. Right. But at the end of the day, the question is, what can it do? And so you need to be able to write programs and run programs and access these systems via the cloud. Mostly that's how it's done today. And measure progress so that when the capability gets to the point where it's being sort of standardized, it's going to be commercial and you need to have the interoperability and connectability and so on, then you can set the formal technical standards.
Fantastic. That makes a lot of sense. And the performance-based standards, that is I think where a lot of standards need to go. Absolutely. Another question is, QEDC has managed to get together industry, government, and really, and in its own way, spur innovation as well and allow for all these companies to do the work that they're doing. So a lot of participants, we have about 20% of the students from US universities. And then we have 80% from around the world. And the question for a lot of them is, how do we then have a quantum ecosystem in our own countries? What leads to this amazing dynamic of startups and government funding and laboratories? How does that get created in other countries?
So I would say I spend more and more of my time interacting with other groups around the world that are seeing the opportunities and creating their own national quantum industry groups or regional quantum industry groups. And I'm actually having regular sort of meetings with some of those. There's a large group in Europe, in Japan, in Canada, in individual countries in Europe. And so just for the same reason that QEDC got together, industry recognizes that there are bottlenecks that are shared. A consortium makes sense when there are these different stakeholders that own different parts of the innovation process. So we definitely are in that space. And then you have critical technology needs or critical workforce needs or critical standards needs that everybody shares. And then again, competitors can come together and successfully help to address those problems. There's a strong feeling, I would say, at the government level that quantum is going to be, the next big industrial revolution, and they don't want to miss out. And so governments are investing in the research, and they want to see that research fall on good soil in their country, and they're trying to help make that happen. And so I think it's fantastic because innovation happens all around the world, not just here in the US, and smart people are everywhere. And it's not like any one country has the advantage right now. It's a big competition. It's a big race. There are opportunities everywhere. And the US government understands that. They've signed a number of agreements with other countries indicating they want to partner because they recognize the US doesn't have the lead in this area, and we're going to need to partner with others. And so at the government level, it's happening. At the industry level, of course, companies, I can guarantee you, the day they are formed as a startup, they're thinking globally. And so everybody is seeing the markets that are possibly around the world, and their supply chains are around the world, and their workers are around the world. So it's a big global quantum community with many kind of pieces. And sometimes it makes sense to get together in a particular country, and sometimes it makes sense to actually work together globally.
Right. And I'll ask a little bit of a higher level question than that as well. If a country wants to have any ecosystem, it's quantum today, it could be a different technology tomorrow. From your experience working in the White House, what do you think spurs that? Is it typically a government initiative and the government says we're going to invest in it? Is it because there's demand for it, like we should see commercial applications for quantum, but then it's too late to invest in a new technology, right? So what typically helps a country become a leader in a new and emerging field?
I think it really is a combination of all the different parts. That's why that sort of ecosystem chart is important. All of the pieces sort of need to have support, and some of them are going to be supported by the government at the earliest stage. And this is an issue for quantum and any emerging technology. There's not a big market yet. So it's kind of amazing the amount of investment that's being made by venture capitalists, by companies like IBM and Google. They're making really big bets on something that currently there isn't a market. And the market actually is still years in the future, perhaps. And so there has to be a sort of patient investment approach. And the government can play an important role at that point in time. So I think you need all of the different partners, and they each sort of have a different perspective and definition of success, if you will. But if a country, feels like it's too late, it's not. Bringing together, and you're probably investing in the pieces, maybe it's not all coordinated. So the more you can do, we have something here called the National Quantum Coordination Office. That's exactly what it does. It tries to coordinate all the different activities that are going on across the government. I actually meet with them regularly because I'm coordinating on the industry side. So we really cover a lot of the space together. And I think coordination is an important part of it too.
Right, an important part that you play. Perfect. I'll ask my colleagues Malu and Raj if you have any questions or thoughts before we close here.
It is great to see you and hear from you. And I hope that all the members of our audience also enjoyed that. And one very important thing that I want to stress and elaborate on is the importance of training the next generation of people, scientists, technicians, students, etc., in this new and emerging field. So if you can please highlight a little bit more on that, that'll be great for our students and participants.
Sure, I'm happy to. I didn't focus so much on the sort of technician piece of the pipeline in my chart, but that is a growing and important element as well. So there are different fields of expertise, you could say disciplines, computer science, materials, engineering, physics. All of these are going to be where students can get education that's going to be relevant. But some people, like to work with their hands. They want to have a shorter path through the education system and can get just a sort of experience. This is a trick, actually. I think this is a challenge, frankly. I don't think there are as many programs in the sort of 2-year technical training environment today that are going to equip students with that quantum expertise. I think students who want that should demand it. Those schools that have 2-year programs are very nimble in a way, much more so than a college or university. And so if they see the demand, both from the employers and from the students, for quantum education programs, they will meet that demand. And so I think that there's a need for the whole spectrum, and it's only going to grow. You can look again at our list of quantum jobs. That's only a subset because we advertise on behalf of our members. You can find other places. There's a website called the Quantum Computing Report that has a jobs list. It's global. It's much bigger list than the list that we have on our website. And you can just see by looking at those job lists, the kinds of skills that people are looking for. And that can help you sort of tailor your education to meet the needs of the people who are doing the hiring. That's always a good way to go.
Also, while you're on that topic, can you please highlight and elaborate the importance of young women to enter this field and also to enter all fields of science? And I think that you are a really good example and a role model for many young women to learn from as well as emulate.
Well, thank you. And you've had great women speakers throughout this program. I was attracted to science from childhood. I had great role models. My father was actually a quantum physicist, as it turns out. And my mother was a math person, so it was in my DNA maybe. But however you come by this passion, you should follow it. And diversity is so important to the success of organizations. If everybody around the table looks the same and thinks the same, then you're looking under the lamppost, as we say. You're all kind of having the same thoughts because you have similar experiences. And so smart companies want to hire people with lots of different experiences. And I hear from our members all the time how hard it is to find people who have some of the skills they're looking for and come from different backgrounds. So I think that it's just wide open now. You cannot just be a woman and get a job. You've got to have some skills. So you've got to go out and get the education so that you have the credibility so that you do a good job once you get hired. And but there's so many opportunities, and I can assure you that all kinds of different companies, large and small, want to get the broadest possible set of expertise so that they can succeed in this emerging but competitive space.
Thank you, CELIA.
Thank you.
Yeah, thank you, Celia. This was fantastic, and looking forward to partnerships in the future and supporting the quantum ecosystem. Thank you.
Wonderful. Thanks very much.
Thank you very much, Celia, for giving us this broad perspective. And that is exactly what we want to give to the participants. The broad overview of quantum computing, other types of quantum, the quantum ecosystem, the quantum workforce, and then additionally give the in-depth knowledge. At the end of our program, everyone knows not only that Grover's search algorithm exists, but also how to implement it. Shor's algorithm, how to implement it. Not only that trapped ion quantum computers exist, but in a few minutes, Caroline will tell you exactly how they work. And on Tuesday, we heard from IBM, how do superconducting quantum computers work? So for our participants, it is not only buzzwords, not only hype, but you know exactly how it works. Not only the software, but also the hardware. And you will implement it yourself in the hackathon soon. We are extremely excited having you today, Celia, giving us the broad perspective. Now we will dive in depth with Caroline, and everyone will be able to convert the knowledge and skills towards jobs. We have several sessions coming up. On Saturday, a career panel with Chris Bishop, the person whom you pointed out as a great career mentor. We have a career fair in 1.5 weeks with a variety of companies. And then the hackathon will be extremely exciting, implementing a green supermarket with Deloitte, or quantum chemistry with IQM, and a variety more real-world problems. Excited to have everyone here the second week of this program. And now we will move to Caroline Figuette, Quantinuum, for a talk about trapped ion quantum computing. Caroline, welcome. You are a senior advanced atomic physicist at Quantinuum, a leading company building trapped ion quantum computers. Before that, you were at the University of Maryland, where you also developed trapped ion quantum computers, a programmable quantum computer, and you tested it on a variety of quantum algorithms with advisor Chris Monroe. You were actually the one who performed the first parallel 2-qubit gate operations in a single chain of trapped ions. And during your PhD, you were also the president of Women in Physics at the University of Maryland. Very happy having you here, and please take it away.
Yeah, thank you so much for having me. Just get my slide shared here. Okay, hopefully those are showing up for everyone. Awesome. Yeah, thank you again. Thank you so much for having me today. I'm very excited to talk to you guys about sort of the very basics of ion trap quantum computing. Again, my name is Caroline Figuette. So I'm a senior advanced physicist at Quantinuum, which is a company that does trapped ion quantum computing, as well as providing a bunch of software services. I work in the commercial products division of Quantinuum, so I help develop products that are then launched for commercial use. And so my goal for today is to give you an overview of how trapped ion quantum computing works in general, and then to sort of walk through an example, which is how we do it at Quantinuum. So my hope is that you'll learn about trapped ions in general and not just about what Quantinuum is doing. So, here we go. Oops, sorry. Yeah, so as I mentioned, so I'll be walking through how to build a quantum computer with trapped ions, sort of in the general case, and I'll be using the Divincenzo Criteria as sort of my guide for that walkthrough. Hopefully you've had a little bit of exposure to those criteria, but I'll be talking through them. And then we'll take a 5-minute break. And then when I come back, I'll walk through Quantinuum's quantum computer. So talking about the architecture of how it's constructed, some of its features, and recent progress that we're making, so you can get a sense of sort of what things people are working on right now. And then finally, I'll very briefly touch on sort of career skills, et cetera, in ion trap quantum computing specifically. Celia probably gave you a much better sort of broader overview, but this will touch very specifically on sort of people and skills that we need in the ion trap field. Okay, so as I said, the way, sort of the guide that we use to figure out what we need to build a quantum computer is something called the Divincenzo Criteria. These were developed in the 90s, and they're sort of basic criteria for developing a quantum computer of any size. And so what you need are, laser point, there we go. So the things that you will need are, of course, a qubit that you can hold, control, do stuff with. You then need long decoherence times for that qubit. You need to be able to do a lot of operations with it and not have the results of your computation just drift off into gobbledygook. You need to be able to initialize the state of that qubit to a well-known initial quantum state. Because if you don't know where you're starting, you can't possibly get to where you're going. You need to be able to measure those qubits when you've completed the computation that you're trying to do. You then also need a universal set of quantum gates, meaning a set of quantum gates that allow you to perform any any operation that you'd want to do, be able to sort of get to any quantum unitary, so that allows you to perform any computation. And then, of course, you need to be able to connect those qubits together somehow in order to be able to perform multi-qubit operations. So I will be, as I mentioned, talking about trapped ions as our qubit. So trapped ions, which are ions, of course, are atoms with either an extra electron or an electron removed, so that they're charged particles. These are qubits that are defined in nature by their atomic structure, which is very nice, because that means that every atom of the same isotope is identical, and they're defect free. They're just like, everything is governed by the laws of nature here. They're also reconfigurable. They can be rearranged and interacted to give you more algorithm opportunities. This is just a nice picture of some of the components that are involved. We'll get into a little more detail about some of what all these things are, but there's a lot of lasers and optics involved. This is a vacuum chamber. There's a little trap inside somewhere, which you can't quite see. Magnetic field coils to help stabilize the magnetic field, things like that. Okay, so I do have a few sort of like pre-quiz questions to hopefully start getting you thinking about how we might actually physically build a quantum computer out of trapped ions. So the first thing to tackle is how do we actually hold an ion so that we can do quantum operations with it. So the first question would be, do you think that we can hold ions with only static electric potentials? Your choices are yes or no.
Please answers on Discord. I see many no's. No, not stable. No. But now no one dares to say yes. But the consensus is definitely no. Oh, yeah, some yes. Very good that you dare. No, yes. I don't know. No, yes. I don't know. More no. Okay, tell us what the answer is.
I don't know is always an acceptable answer, for the record, but glad to say the consensus was correct. The answer is no. The equations that govern electricity and magnetism, in particular Maxwell's equations, do not have a solution that can statically hold a single charged particle in 3 dimensions, which is what we need to do. So instead we use something that's called a pseudopotential. And so what we use is a combination of RF and static fields to confine an ion in 3-dimensional space. So what the RF does is it allows us to construct something called a saddle potential, which is, if you sort of imagine like a U in one direction and then an upside down U in the other direction, and then there's sort of the splat part in the middle, so it looks like a saddle. We construct a potential like that, and then using RF, we're able to alternate that. And if you do that fast enough, the charged particle in the center, as far as it's concerned, it feels like it's sitting in a bowl. And so that allows us to confine it. And then that actually only covers 2 dimensions. For the 3rd dimension, we then use static fields generated by DC electrodes to confine the ion in that 3rd dimension. And then that also gives us some fine tuning control as well on sort of the shape and of location of that potential. So the way you can think about it is we have, this is sort of a quick diagram of something similar to what we call a 4-rod trap, where you simply have some RF sources, and then you've got your DC controls, and that generates your pseudopotential and allows you to trap an ion at the center, at the location that we refer to as the RF null, which is sort of that flat part in the middle, in the center of the bowl. If you're not on that RF null, your ion is going to experience something called micromotion, which is, you can sort of think about it as, because that potential is alternating, it's sort of swirling things around. So you can think about, like, if you've got like a bowl with a marble in it, and then if you swirl the bowl, the marble also swirls around. It's sort of like that. So if you're right on that null, you're not really moving, but if you're off that null a little bit, you're going to experience some jiggling. And it turns out that if we do that by accident, we generally don't want that. But we sometimes do it on purpose, which I'll get to in a whole bunch of slides.
For the non-physicists among the participants, what is RF? What does it stand for?
Oh, sorry. RF stands for radio frequency. Just think about it as yeah, it's a rapidly rapidly alternating frequency, sort of like the difference between AC and DC current, where DC is just like your electrons are just moving along nicely in a line, and in AC current, your electrons are jiggling back and forth. So with an RF signal, like you would characterize it as a sine wave with some frequency and amplitude. And so that is providing your alternating electric field. Yes, I am, oh, sorry. Thank you for bringing that up. I am going to get into the physics a little bit of this because I know that there's a very broad audience for this. So what I've tried to do is, for this first set of slides, there is a decent amount of physics that I try to get into for the folks who want that. But at the bottom of most of the slides, I have text in red. So if you do get a little bit lost in some of the physics, you can hopefully just hone in on that red text, and that will give you the big takeaway from the slide so that you're prepared for the next one. Yeah, hopefully most people will be able to follow this pretty well. And then just the final point about this is, so you can actually take these RF and sort of DC sources, and you can flatten them like this to construct sort of the, basically flatten them onto a 2D surface. And that turns into electrodes on a surface trap. And so like this, here it is. This sort of arrangement is sometimes referred to as a 3D trap because you have your electrodes in 3 dimensions. This is a 2D surface trap. Most companies and a lot of academic groups use these surface traps to actually trap their ions for a variety of reasons. But there are plenty of folks who do the 3-dimensional model as well. Okay, so we're now holding on to our ions, but now we actually want to use these ions as qubits. So the next question would be, how do you think quantum information is stored in a trapped ion? And so your options are the hyperfine energy levels of your trapped ion, highly excited Rydberg energy levels, vibrational energy levels, or in its pockets.
Several answers in the chat already. Will it be a superposition of answers again, as Nasser pointed out, with the correct prefactors of 1/√2 for the 2 previously? I see B, I see C, I see B, maybe C, A, B, no D so far. Many B, many C. Oh, someone also likes D. Again, and I don't know always the right answer. B, C. Some people wonder now about D, C, B. Could you, in your explanation, Caroline, also compare it with atom computing? We had a talk by them on Monday where they used neutral atoms and put it into that perspective.
Oh, yes. Okay, so the answer is A, the hyperfine energy levels. So the hyperfine energy levels of an atom are, there will be some diagrams coming up, but basically, in an atom, if you draw out all of the energy levels that you can possibly be in, once you take into account the electron spin, all the electron orbitals, and the nuclear spin, that sort of full diagram gives you the hyperfine energy levels. And so what we can do is pick two of them and call one of them 0 and one of them 1 and say that is our qubit. Marlu was thinking ahead and mentioned atom computing. So yes, definitely honorable mention for the folks who said B. Rydberg energy levels is how some neutral atom quantum computers store their quantum information. As for D, that of course is a Lord of the Rings reference. So also shout out to the folks who picked that. Okay, so we have trapped ions. We want to use them as a qubit. So one thing, of course, is there are lots and lots of different elements and then isotopes of those elements out there. And we want, we have to pick one. There are actually a bunch of different species that you could pick for a variety of reasons. Sort of every sort of candidate species has kind of upsides and downsides. But at Quantinuum and actually several other companies and academic groups as well use ytterbium and specifically ytterbium-171. So from here on out, I'm going to use ytterbium as sort of the qubit for all these explanations. It provides a nice example. It's also the one I'm most familiar with because it's what I did my grad work with, and it's also what we're using at Quantinuum. Basically, so as I mentioned, we've got these hyperfine energy levels, and we use them. We pick basically two of them that are in the ground state manifolds, and we pick one of them to be our 0 and one of them to be our 1, and then that is our qubit. And so that is how we're storing our quantum information. And again, every ytterbium-171 is the same as every other ytterbium-171 qubit. And then we're able to use lasers to address, entangle, and measure these qubits. The other nice thing about these qubits is we have very long coherence times. So atomic energy levels don't drift over time. Actually, the only way that they would is if the fine structure constant of the universe turns out to drift over time. And if that is the case, quite honestly, we have other problems. But to the best of our knowledge, that does not appear to be changing with time. So therefore, these atomic energy levels are not drifting over time. The errors that we get, sort of our the decoherence that we do get, basically arise from things external to our actual qubit. So from controllers, if we haven't built them well enough, and then also from the external environment, things like if your local magnetic field changes or drifts over time, or other things of that nature. And we also understand these errors from a fundamental physics level. Getting the engineering right, of course, is another problem. So sort of your takeaway is the secret with trapped ions is to precisely capture, control, and manipulate these ions in order to do quantum operations. Okay, so if you remember from our Divincenzo criteria, we now have qubits that are well characterized with long coherence times. So now we need to be able to perform state preparation, right? We need to dependably get them down to an initial state that is coherent so that we can proceed from there. So I will just quickly, briefly explain. You'll see a bunch of these energy level diagrams as I go through. So this diagram represents a single ion, and it's actually a subset of its entire electronic structure. The energy goes in the vertical direction. So as you go up, energy gets higher. Then, so we've got these numbers over here, 2s1/2, 2p1/2. The S and P, if you remember, like maybe high school chemistry, which hopefully y'all have taken, but if you remember that, like there were the orbitals that you might have studied, where you had like the S orbital, which was the sphere, and then the P orbitals, you start getting these weird like loby things, and then you're the D orbitals that were even weirder. That's what these letters are referring to those electron orbitals. That's sort of another layer down of your electronic structure. And then the 1/2 here, that refers to the spin of the nucleus, which different isotopes will have different nuclear spin based on the composition of that nucleus. So it is isotope specific. And then over here, these F numbers, these refer to the hyperfine splitting. So again, the hyperfine splitting is particularly once you take that nuclear spin into account, that's sort of the finest, sort of the most detail that we get for constructing the electronic structure of an atom. And then the sort of horizontal axis here is basically the splitting that you can get if you have a magnetic field gradient present. And each of these columns is sort of a different, what we refer to as a magnetic field quantum number, which I'll sometimes shorten as MF, where the center is 0. This is MF equals -1. This is MF equals 1. And if there's no magnetic field, like these 3 states will all be the same energy. But if you do have a magnetic field, what we say is the degeneracy breaks, meaning that instead of being the same energy and therefore indistinguishable, they actually do shift a little bit in energy, and so you can distinguish between them. Okay, so that is how to read an energy oval diagram 101. So if we want to prepare an ion to use for a quantum state, or for a quantum computation, actually the first thing that we'll do is some laser cooling techniques, which I won't get into in detail, but what they do is bring the ion to its motional ground state. And this is a cooling operation. We don't do this with cryo, we do this with lasers. And it brings the ions down to very, very, very close to absolute 0. And the techniques that we use are things like Doppler cooling and sideband cooling. And if those are things that you don't know anything about, those are the words that you want to Google later on. But those are techniques that cool down to the motional ground state. And then in order to prepare the qubit into the 0 state, we're going to use a technique called optical pumping. And so now this is to get us to the electronic ground state. And so what you do is after ground state cooling, you're going to be in potentially any one of these states, F equals 1 level, the S1/2 manifold. And so you apply a laser pulse that addresses all of the transitions between these states and then the states in the F equals 1 P1/2 manifold up here. Each of these lines is a different energy state. And so you apply this laser pulse, and that excites the atom into one of these higher energy states. And after that excitation happens, it will then decay down to a lower energy state. So in atomic physics, we have something called selection rules that basically, there's a lot of math that goes into them, but basically they tell you sort of a certain set of rules of like what transitions are allowed under what circumstances. And if you're so if you are in an excited state, you can end up basically decaying down spontaneously with something called spontaneous emission into a lower energy state. And if we pump up into these states in ytterbium, the decay will go down to the S1/2 F equals 0 state, which is what we've designated as the 0 state for our qubit. And so we call that's a technique we call optical pumping that brings us down to this electronic 0 state. So that was a bunch of physics. Again, if you got a little bit lost, that's okay. The thing you need to know is that laser control of atomic state allows us to initialize our qubit to our designated 0 state. Okay, so the next thing that we need, we've got state preparation. Now we need measurement at the end of our computation. So again, we're going to do this with laser pulses. And so what we can do now is we're going to apply a laser pulse that is resonant with the transition from our 1 state, or our qubit 1 state, to this f equals 0 p1/2 state. Again, because of the selection rules, so we'll excite this to this higher state, and then when it decays down, again through spontaneous emission, it will actually emit a photon at that same frequency. And so that if you're in that 1 state, that it'll be excited, and then it will decay down and emit this photon. And that's something that we can detect on a photon detector. However, if you were in the 0 state at the end of your operation, when you apply this laser pulse, there's sort of no state for it to go to. Therefore, it doesn't actually get excited. Therefore, it doesn't decay, and no photon is released. So what that means is that when we apply this measurement laser pulse, we can see that the 1 state is bright, it's releasing photons, but if it's in the 0 state, it's dark, it's not releasing photons. And we can count those photons on photon detectors. Okay, so the next thing on the Divincenzo criteria, of course, is we need a universal gate set. And so for trapped ions, that means single qubit gates and 2 qubit gates. So our single qubit gates use, so there's a couple ways that you can do this. Most groups use something called stimulated Raman transitions with lasers, where you use a laser pulse that actually has what we refer to as sidebands, meaning there's multiple frequencies on the same laser beam. And so the stimulated transition will, so you're in a coherent, let's say a coherent 0 state, you're able to excite up to what's sometimes referred to as a virtual state. And then the other frequency on the laser, the other sideband, will cause what's called a stimulated transition, where it then brings it. So this isn't a spontaneous decay. This is sort of a guided tour, where that laser frequency brings it back down to the 1 state. So we refer to this as a virtual state because it's sort of like being excited up to this excited state, but the state doesn't actually exist. You're sort of creating it with the 2 laser frequencies that you're applying. And so that allows us to drive this transition between our qubit 0 and our qubit 1. And the other nice thing about this is that you can actually do arbitrary angle rotations. So hopefully you've already had a little bit of an intro to something called the block sphere, which is a representation of a single qubit state on the surface of a sphere in 3-dimensional space. And so if you apply one of these laser pulses to do a single qubit gate, you can actually control where on the block sphere you end up very easily, because the duration of the pulse, you can also do it with the amplitude, but most people do it with the duration because it's easier. But the duration of the pulse will set the theta of that rotation, and then the phase will set the phi. And so that allows you to perform rotations around sort of any axis in the XY plane. And then that arbitrary angle rotation, like you weren't just limited to like pi/2. That arbitrary angle rotation allows you to get to any point on the block sphere with fewer pulses than if you didn't have that limitation. Another option is you can also do direct microwave gates. For ytterbium, the stimulated Raman transition requires a 369 nanometer laser that's in the near UV, so it's a little bit purpler than purple. But the direct transition is 12.6 gigahertz. So you can do that with microwave pulses. So you can also just directly drive this. As with everything else, there's sort of upsides and downsides to both of these. The work that I've done has all been with the stimulated Raman transitions. So That's what I'll talk about. But again, so the big takeaway here is that we can perform single qubit rotations on ions, and with them we can perform any single qubit unitary. And that's important toward our universal gate set, because the universal gate set generally consists of a CNOT gate and then like whatever, some set of single qubit operations, and we can do all of them. So this sort of covers all of the single qubit operations that you need for your universal gate set. Okay, the next thing that we're going to need are 2-qubit entangling gates in order to fill out our universal gate set. And so in order to do that, of course, we have to connect those qubits. So how do you think we connect and then exchange quantum information between 2 trapped ion qubits in order to do a 2-qubit entangling gate? So your options here are, it's done because you've got a shared laser beam, because you create a molecule, because you use motional modes of motion, or with the internet.
It looks like no one is choosing D so far. Many A, C, A, C, notional modes, A, B, C, A. I think you can liberate us, Caroline, and tell the answer.
Okay, so the answer is C, motional modes. So if you have...
It was not chosen by too many, so we will need to hear a good explanation. Most of people chose A.
Okay. You actually don't need, the shared laser beam helps, but you don't actually need it. And I did that in grad school. I performed 2-qubit gates in grad school without shared laser beams. But the answer is actually the shared modes of motion. So if you have multiple ions, which remember are charged particles, trapped in the same potential well, they form what we sometimes refer to as a linear crystal, meaning they're sort of in a row. And then because they're charged particles and they're all charged the same way, the Coulomb forces then push, like they repel away from each other, so they're pushing each other apart. And then with the potential well that you're trapped in, that acts as a restoring force that pushes them back together. And so you can think of that as each ion as a ball that's connected by springs, where the springs are both the repulsive force and that restoring force. And so if you sort of vibrate that set of balls on springs, you get what are called normal modes of motion, which are sort of the resonant frequencies at which that chain will move. And any motion that occurs can be described as a superposition of all of those frequencies. And so this then means that all the ions in that well participate in these motional modes. They all interact with them, and therefore you can use that as an information bus to transfer quantum information. The reason it's not a shared laser beam is it does help a lot, particularly if you use the same laser source, but just being in the same, just being in the same laser beam doesn't actually allow you to transfer information, because there's yes, you're in the same beam, but there's no actual connection there. Okay, hopefully that is clear to folks, but I will now get into this in a little more depth. So the way that entangling gates are done with ions, there's a few ways that you can do it, but most folks do something called a Molmer-Sorensen gate, which and a lot of the other schemes have some sort of similar type of thing where they're using these motional modes and addressing them in order to make this transition happen.
And could you briefly go back to the motional modes? You showed it earlier, how it exactly works with a slide. People ask again, what do you mean by motional mode? Is it the same with vibrational mode?
Yes, it is the same as a vibrational mode. So I don't unfortunately didn't put together a good little animation for this. But yeah, you can think about it as, so if you've got 4 ions in a trap, I'm going to do this with my hands here. If you've got 4 ions in a trap, right? There's different motional modes in each direction, but the axial normal motional modes are, they're either all sort of going back and forth together. We call that the common mode. There is a tilt mode where they're sort of going like this, like tilting back and forth around sort of a central point. I guess I'm demonstrating this in an axial manner slightly, but I'm only so good at doing this with my fingers. You then also have what's the next one? There's sort of this like funky mode where like you're doing this, where it's like the 2 ones in the middle are sort of moving opposite from the outside ones. And then there's what we sometimes call the Egypt mode, because it looks like you're doing the little Egypt dance, where the two on the outs, like they're sort of moving like this. So those are like and then if you go up to like a chain of 5 qubits, those motional modes look a little bit different. So that is how you end up with these shared motional modes. Does that so you can sort of see how you because everyone is sort of moving together, you can then actually quantize, you can do something, so you can describe, it's sort of in quantum world, right? We like to quantize things and then describe sort of the number of that, like sort of the number of like particles that describe that. So for motion, that's phonons. A phonon is a sort of single particle, as it were, or like a single a single quanta of motion or of vibrational energy. And so you can split that into because everything is quantized. You can again sort of describe energy levels of as you add one more quanta, right? You can draw an energy level diagram that shows that, and then be able to transition between those different energy levels, right, in a discrete manner, as we do. And so what that means is that in addition to our electronic structure, you also do have the energy levels due to having more or less vibrational quanta in your system. And so that is what we're addressing with the Mormel-Sorensen interaction. So we're using a laser that has both a red sideband, which means that it is detuned to a slightly lower frequency, and then a blue sideband, so it's detuned to a slightly higher frequency. And the red sideband allows you to transition to a state where, if you're starting in with both qubits and 0 in your electronic state, and then n is the number that we use for the number of phonons in the system. So this is the number of discrete vibrational energy packets in the system. So you can use this red sideband to couple to a slightly detuned state where one of your qubits has had its electronic state flipped, and also one quanta of vibrational energy removed. And then the blue sideband couples that state to a state where the other qubit's electronic state has also been flipped to 1. And then its vibrational energy state has been restored, has had a phonon returned, and then it is brought back to sort of the original number of phonons in the system. And then this is actually symmetric. You end up sort of coupling to every equivalent of the state, where the blue sideband is also coupling to the other qubit state flipped, adding a phonon, and then the red sideband removes that phonon again and flips the other spin. Actually, if you do a full diagram of this, you end up with like another virtual state here, another virtual state here, and another set of the blue and red, but I left those out because the diagram gets really busy if you do that. So hopefully that makes a little more sense. Is there more confusion in the Discord chat? Or are folks doing okay with this?
Yeah, go ahead.
Okay. Again, I know it's a lot of physics, but the takeaway is if we do this scheme, we get an entangling gate, right? Where we, if we start in the 0, 0 state where both qubits are 0, we're going to end up in a superposition of 0, 0 and 1, 1. And if you actually add a couple of additional single qubit rotations, this becomes a CNOT gate. So a sort of entangling 2 qubit gate is, with a few additional rotations equivalent to having access to a CNOT gate. And so if we remember Divincenzo Criteria, right, we need a universal gate set. So the big takeaway here is that we do get a universal gate set with ion qubits. And the way that we do that is we have, from a few slides ago, arbitrary angle single qubit gates, which allow us to do any single qubit operation, plus these entangling 2 qubit gates. And that constitutes our native gate set. And with that, we can perform any quantum gate that we want to do.
And maybe still some clarifying questions.
Oh,
Sharma asks, so the phonon energy matches the 0-1 transition energy, is that correct?
Phonon energy matches 0-1 transition energy. A good question. I tend to think of them as sort of being on different axes, and you're addressing them in different ways. I think I'm gonna have to think about that, actually. Like, what's a good way to answer that? Yeah. Can I get back to them? Yeah. That might be, I might need more diagrams than I have access to really get into that.
Great. Yeah.
Okay. Sorry. I was mostly hoping to just sort of give a sense at least of the physics. But I could give entire talks on this thing. Obviously, normal sorts of gates, like there's a lot that goes on. There's a lot of ways that you can sort of tweak and adjust it to make it suit your needs better. But okay, in the interest of time, we'll move on to the next thing. So the final thing from the Divincenzo criteria is, of course, we need to be able to connect many qubits together in order to do anything interesting. So for ion traps, the next natural question is, what is the architecture that you're going to have in order to connect many qubits and have an ion trap quantum computer? So my next question for you guys is, how do you think we could construct the overall architecture of a trapped ion quantum computer to connect many qubits? So option A is a long chain of ions in a single trapping potential, and then you've got individually focused laser beams that can be turned on and off that each address a different ion. Do you have a long chain of ions also in a single trapping potential, but now you've got a few focused laser beams that can be moved to different ions? Do you have large magnets that create a gradient in order for you to do individual addressing with microwave gates, which I briefly mentioned earlier? Or do you have many small trapping potentials, each of which hold a few ions, and then the ions are moved around the trap using transport?
On the Discord server, I see D, 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 C, A, C, D. No B so far. A, a B, a C, quite some Ds. D and C are most common at the moment. Some I don't know. So we are here to learn. Great. C or D, some A's again. Most is C and D, a little bit of B now, a little bit of A.
All right. Well, bad news was that was a trick question. The good news is every single one of you is correct. All of these are actually valid and or valid ways of constructing a larger scale ion trap quantum computer. And in fact, all of these, to my knowledge, are actually currently in use, either by some company or some academic group. So again, we have all these architectures. They're all in use somewhere by one of these quantum computing companies, and or by the many university and government research labs that are also doing ion trap quantum computing. Which, if I tried to list them all on a slide, we'd be here all day. There are many of them, but to my knowledge, these are sort of the main companies that are doing ion trap quantum computing as a hardware platform. I actually, this with a long chain of ions with individual focus beams that can be turned on and off. This is what I actually did in grad school for my grad work, was a system based on this kind of architecture. And now that I'm at Quantinuum, this is the architecture that we use at Quantinuum. And I will also say that all these architectures allow for either full or very high qubit connectivity. So what that means is that as you know, as you go to many qubits, you can actually do gates directly between any pair of qubits, rather than having to sort of, you know, if you want to connect a qubit to, or like do a 2-qubit gate between this qubit and then a qubit that's over here with a bunch of qubits in between, you have to end up like swapping your quantum information to sort of move the quantum information over closer to the other qubit to do that gate. With full connectivity, you can just do the gate directly between those two. And that of course gives you a lot of efficiency in terms of quantum algorithms. So obviously that is of great interest to be able to do that. Or at least have a lot fewer of those swap gates, as they're sometimes called, to swap the quantum information between qubits. If you don't do nearly as many of those, you're going to have a much easier time of things because you don't have to do nearly as many gates. So yes, multiple possible architectures. Okay, so we've now walked through the Divincenzo criteria for how to build a quantum computer in general. I'm going to do a brief intermission so folks can take a break. And when we come back, as an example of sort of how all this might come together, I will walk through Quantinuum's quantum computer to show you how our architecture works and sort of bring it all together into a real world system. So I will, Marlu, do you have a timer for 5 minutes, or I can set a timer and just restart in 5 minutes?
Yeah, let's just do briefly a few minutes, and then when you are back, Caroline, in the meantime, everyone can ask more questions. I will compile the questions for afterwards, and then we will restart in a few minutes.
Excellent.
Could you bring up slide 16 in the meantime, Caroline, if you're still there? People want to view it again. Wonderful. Yes, thank you, Mohammed. We will ask if slides can be shared, and otherwise if other resources can be given so you can keep on learning more about ion trap quantum computers. Great, many questions. Yes, very good question. It's also about the comparison with other systems, with superconducting qubits, neutral atoms. What are the differences in the techniques that we use to make them? What I always find so fascinating myself is that we need a lot of classical physics to make all quantum happen. And you need a lot of, or it is good to have the basic physics knowledge in the classical sense to build eventually a quantum computer. And here a lot of atomic physics. You see that people needed in quantum is very diverse. We need physicists, electrical engineers, computer scientists, and we all need to know a little bit of each other, but we can't know everything. If Caroline comes back for a few more lectures, it will be so in depth, which is great for the physicists, but computer scientists might know enough after this lecture, and vice versa. I'm a physicist myself. When I learn about Shor's algorithm, just the basics, it might be enough, while the software engineers, of course, need to dig much deeper. And like this, we learn to speak our languages, each other's languages, and then we can collaborate and work together, join forces to build a quantum computer. Caroline, when you are ready, just bring up your video and we will get started again.
Okay, I've got another minute on the clock, but were there, I missed some of what you said, Marlu. Were there questions that came up that?
We will do them at the end.
Okay.
And everyone is very curious to hear more. So looking forward to the second part of your talk.
Glad to hear it. Okay, give folks just a couple more minutes or a couple more seconds to get back from refilling their water bottles or whatever it is that they're doing.
In the meantime, participants were wondering how precise can you tune the pulses and how precise can you move on the block sphere?
Very. And of course, the more precisely we can do it, the higher our gate fidelities are, and therefore the better our quantum computer. Do I have numbers for this in my head? Good question. Actually, I think I've got, for Quantinuum specifically, I do have a slide in a bit that I think has sort of our current resolution for how good we can do the single qubit rotations in units of pi, which I think is pi over 500 is our current. I'm hopefully recalling that number correctly. I might have to correct myself in a few slides. But yeah, that is about how precisely we can do single qubit gates, and that translates into fidelity numbers that I'll also show in a bit. But in general, ions are sort of easier, I think, than other qubits to get those high fidelities. Most, if not all, of the sort of world records for qubit fidelities come from ions. And you know, I say easy, but in the sense of, you know, given what ions hand you, which is of course the fact that their qubit frequencies, like internally inherently don't drift. It's a matter of how well can you control your laser frequencies and phases, how well can you you know, time the pulses necessary to perform these operations relative to each other. That's actually where the errors come from. It's sort of on our end of things, us as imperfect humans who can't build perfect lasers.
This was a great question by two people. Very insightful answer. Thank you, and looking forward to the second part of your talk.
Okay, and speaking of that, I will move on to that. So yes, for the next little section, or not so little, I'll be walking through specifically, also Marla, there aren't any more questions. So this part, I'll be walking through sort of Quantinuum's quantum computer, how our architecture comes together to construct a full trapped ion quantum computer, some of the features of it, and some recent progress to sort of show like what are some things that people are working on as examples. And again, this is an example. There are lots of other companies and academic groups out there who are also doing this, who are doing it in different ways. But hopefully this will provide a nice example for you. So first, I'm going to briefly talk about Quantinuum itself, since I haven't done that yet. So Quantinuum is a company that is now it is a combination of what was formerly Honeywell Quantum Solutions, or HQS, and Cambridge Quantum Computing, or CQC. The merger closed last November. So we've only been a combined company for 8 months now. This is very exciting, of course, because it allows us to bring together from HQS the ion trap hardware expertise that we have with the sort of high-level quantum software expertise that CQC has. And it's a global company. We've got offices in the US, the UK, Germany, and Japan, with about 420 employees right now, 330 of which are technical. So we're a very technical heavy company. We have dual headquarters in Broomfield, Colorado, which is where I work, and then also in Cambridge in the UK. The hardware side of things is based primarily in Broomfield, with another sister site in Minnesota. And then the software side of things, the CQC side of things, is headquartered in Cambridge. And so we've been continuing to sort of integrate the company and working together to sort of enhance each other's or come together as a single company. And in fact, we have actually already launched our first 2 products as a combined company. Quantum Origin, which is a cybersecurity offering that allows us to generate provably non-deterministic random numbers for crypto key distribution generation. And so that actually uses entropy from the Quantinuum 8 series quantum computer, which is our hardware. So that's a really nice sort of meshing of using our hardware and then to generate the entropy needed, and then our software expertise to turn that into a cryptographic key product. And then we also now have Inquanto, which is a computational chemistry software platform that uses quantum computers that folks can use. And so, yeah, in total, we bring together this really nice full stack capabilities where we have a really expert quantum software team working together with our really expert hardware team. And I am on the hardware team, if that wasn't clear. So as I mentioned, the architecture that, within Quantinuum's hardware, the architecture that we use to construct our ion trap quantum computer is this architecture where we have many potentials with just a few qubits or ions in each, and then we're actually able to physically move them around the trap. This is sometimes referred to as QCCD architecture, which stands for Quantum Charge Coupled Device. This was proposed by the NIST Ion Storage Group back in the 90s. So we've been able to sort of turn that into a real working commercial system that customers can run jobs on. So this is sort of a diagram of our trap. There's a nice little picture of it. And so, as mentioned earlier, our qubits consist of ytterbium ions, where we're using 2 of the hyperfine energy levels as our qubit. And then something I've glossed over a little bit is that we, in addition to our qubit ions, we actually co-trap them with barium-138, which is another ion that we actually use, we sometimes refer to them as spectator ions, because they are not qubits. We instead use them to cool our ytterbium ions in the middle of circuits. So if you're, you know, as our ytterbium ions are moving around the trap, they might start heating up a little bit, right? And that's not good. So if we've got these barium qubits co-trapped with them, they're in the same potential well. So we can use something called sympathetic cooling, where we actually use lasers to cool the barium ions. And of course, cooling is just a matter of reducing the number of motional quanta in the system. And how do those, of course, are like they live in the motional modes. And of course, those motional modes are shared with ytterbium. So by cooling with barium laser pulses, the ytterbium ions also get those motional quanta removed. And so they are cooled without disrupting the actual quantum information in the system. Because if you try and cool the ytterbium directly, you're gonna destroy your nice quantum state. You're gonna just, you know, completely screw up your computation if you try and do it in the middle of the computation. But we can do that via barium, and that's a technique that that other folks are using as well, having sort of their like a qubit species and then a spectator ion that is a different species, so that its laser pulses don't really do anything to your qubit species, but you can use sympathetic cooling to cool your qubit ions and keep them nice and cold. And so the architecture that we're using with this QCD architecture, so yeah, as mentioned, we've got these identical high quality qubits, which are ytterbium 171. We hold them in dedicated interaction zones. So in this little diagram, the blue areas are what we refer to as gate zones. And in those zones, we're able to perform the laser pulses that do gates. And then we have these very short chains of either basically a single qubit and its buddy and its barium buddy, or two qubits and they're both their barium buddies. So with these short chains, we're able to then move them around physically. I'll get a little more into that. With the short chains, that also makes it easier to do really high fidelity quantum gates. And then in order to actually gate them with each other, we move them around between the zones. So to sort of walk through this whole architecture. So of course we have, at the heart of our system is the actual ion trap. So this is a nice zoomed in picture of the actual trap that we're using on our current H1 series system that we have available for commercial access. And so this is a microfabricated chip with metal layers that create these electrodes. And so in this box, you can see here each of these sort of little rectangles. Those are the actual electrodes on the surface. Those electrodes, and then sorry, the long things here, those are the RF rails that generate that alternating pseudopotential that I mentioned a bunch of slides ago. And then the electrodes provide DC signals that allow us to move the ions around and sort of more finely control what's happening in the trap. So the ions are then held above the surface trap. And then just to give you a sense of the size, this trap is about like the chip that it's on is about the size of a quarter. So this is clearly microfabricated. And in fact, it's microfabricated at Honeywell. We're very proud of the engineering that goes into it. We're also, it's you know, a big advantage for us that we're able to sort of effectively do this in-house or with our former parent company. And that gives us a lot of opportunities and options to sort of continue engineering these traps as we scale up to bigger systems and move forward as a company. Okay, so to sort of walk you through sort of how we use this architecture and how we perform quantum operations. So the first thing that we have to do is load ions. And what happens is a neutral ytterbium atom is launched into the trap. And then we use a laser to ionize that atom. So strip the electron off And now this is an ion, which means that it's a charged particle. And so it's now responsive to those electromagnetic fields that we're going to use to trap it. So with our RF and DC fields, we create a potential that then traps and holds our ion. And then we can repeat that process to trap many, many qubits. So next what we want to do is be able to transport our qubits around the trap and perform gates. So the DC electrodes, so again here, these long guys, these are the RF rails, the little short things, those are our DC electrodes. So with those DC electrodes, we can adjust the voltages on those electrodes to move the ion to different zones along the trap. And so I might move this to what we call a gate zone, which is where we can actually perform quantum operations. And then I'm going to use a laser to operate on this qubit in that gate zone to perform a single qubit operation. As mentioned earlier, right, this is another representation of the block sphere. With that laser pulse, I can move I can adjust sort of the qubit's location to anywhere on the block sphere. And those operations are simply rotations on the block sphere. And again, we are not limited to simply pi/2 pulses. We have these arbitrary angle rotations. Now, the next thing that I might want to do is perform a 2-qubit gate between 2 qubits. So we're going to merge two separate trapping potentials into one so that our 2 qubits are now in the same potential. So we have these individually trapped ions. I've been doing other stuff with them, and they're in their own separate potential wells. And then I can use those DC electrodes to merge their potentials into a single well. And then once they're in their single well, remember they're sharing emotional modes now. And that means that we can perform a 2-qubit gate with them. So we apply the necessary laser pulses to perform a 2-qubit entangling gate between them. And so once that happens, I've now entangled them. I am going to, again, use those DC electrodes to split that potential well back into 2 separate ones. And so now I can move these ions apart. And then I can transport them elsewhere in the trap to interact with other ions. So I just did a gate between these 2, and now maybe I want to take this guy elsewhere and do a 2-qubit gate with someone else. And so this ability allows us to have that full connectivity that I mentioned earlier, where we're able to move the ions around the trap so that we can interact any qubit with any other qubit. Okay, to sort of walk you through a simple sort of example quantum circuit. So here I have 3 qubits, red, green, and blue. And so this is the quantum circuit that I want to do. Hopefully you've all seen at least a couple quantum circuit diagrams by now. So of course, the first thing that I need to do is I load the trap, right? I've got red in a gate zone, I've got green in a different gate zone, and then I've got blue. So the gray here, those are gate zones. The white in between, those are storage zones where we can't do quantum operations, but we can hold qubits to sort of be out of the way while we're doing stuff with other guys. So I load up my qubits, and then I use laser pulses to initialize them all to the 0 state. And then now I want to do a single qubit gate on the red and the green qubits, right? This is a Hadamard gate, which is the single qubit gate. And so these guys are in their gate zones. I can just apply the relevant laser pulse in order to perform this single qubit Hadamard gate. Now, for my next operation, I want to perform a 2-qubit gate, right? This is a CNOT gate. We do this by performing a 2-qubit entangling gate and then a couple of single qubit operations. But basically, the important thing is it's a 2-qubit gate. So in order to do that between red and green, we have to bring red and green together into the same zone, into the same potential well, and then apply a laser pulse. So I'm going to move green over to join red. Now they're in the same potential well. And so now to do my 2-qubit gate, I can apply a laser pulse to both of them that now performs that entangling gate. And again, because they're in the same potential well, They share those motional modes, and so they're able to do the gate. So now what I want to do is I actually want to do a gate, another 2-qubit gate, but now between red and blue. So I have to get red and blue together into the same gate zone somehow. So what I'm going to do is perform a swap or flip operation. And this is different from a logical swap. So a logical swap, which you may hear about from other other folks with different types of qubits, where because they don't have full connectivity, right, they have to sort of move their quantum information over from from a qubit that isn't connected to a qubit that is connected in order to perform that gate that they want. And that's a logical operation that requires 3 2-qubit gates. This is not that. This is a physical exchanging of 2 qubits. So with this flip, I actually physically move the red guy around the green, and then I'm going to shift it over to this other gate zone to join the blue. So now red and blue are in the same gate zone and the same potential well. So again, I can apply a laser pulse to them, and that performs their 2-qubit gate. So I now, so that allows us, again, this sort of full connectivity where I can physically move the ions around the trap in order to entangle them with any other qubit in the trap. So now the next thing that I want to do is measure the green qubit. And this is actually because, I'll get into a little more detail on this, but I can actually do this in the middle of a circuit without disturbing the other qubits, because the green qubit is in its own, the green qubit is in a separate zone. So I can apply a laser pulse that performs a measurement on the green qubit, and then we can take the results of that measurement and store it in some classical register. I can then reinitialize the green qubit with another laser pulse and start using it again for more circuit. And I can use this classical register actually to then perform gates on other, or like as a conditional to perform gates or not on other qubits as I move forward with my circuit. And this feature is particularly useful for things like quantum error correction, so that you can actually, read out one particular qubit and then condition later gates on the results of that readout, which allows you to, without stopping the quantum circuit that you're doing, correct errors as you go. Okay, so to give you sort of a real world view of some of these transport operations, since those are, something that is, not everyone does transport, but Quantinuum does. So it's sort of a particular feature of ours. So to give you a sense of what this actually looks like physically, so I've got 2 little videos here of what some of our transport operations look like. So this first video is a video of a split and actually a transport, a split, and or a shift, a split, and a combine. So each of these dots is an ion. It's got a laser shining on it such that it is then generating photons that we can see on the camera. So we've got a gate, basically a gate zone here and a gate zone here. And so when the video restarts, so I've got a qubit here and a qubit here. I'm going to move this qubit over into the same zone as this guy. This is actually, it's not like teleporting over here. It is actually moving, but we don't have like a laser shining in here, which is why you don't see it. It also moves pretty quick. So this guy travels over here. Now they're in the same zone, but they're still in separate potential wells. And so now I have to do a combine operation. And when it's the single dot, that's actually when it's in the same, they're both in the same potential well, but they're so close together that you can't actually see them as 2 separate dots. You only see it as a single dot. And then after you can then resplit it, and then you can move the ions elsewhere in the trap. And then the other sort of transport operation that I've got a nice little video of here is the swap or flip. As I mentioned earlier, it's not the same as the logical swap. This is a physical swap where I've got 2 ions here, and then I'm rotating them around each other. And that the fact that we can reorder the ion positions, this is what really gives us our full qubit connectivity, because it means that I can, move this guy pass this guy and then move it on elsewhere in the trap to link up with any other qubit and give us our full connectivity. Okay, so another really nice thing about the architecture that we're using is it makes it really easy to do parallel quantum computing. And so that means that we can, because we have these sort of multiple separate gate zones, right? So here's a picture down here of, I think it's a single ion in each of 3 separate zones. They're physically far apart. And so that means that if we're, trying to do a gate on 2 separate ions, that, like we can do that in parallel, and we have extremely low crosstalk. And so that gives us much faster algorithm execution time, as well as, of course, greater options for qubit connectivity. And so this picture here is, this is actually from the H0 system, which is our previous commercial system where we had 3 gate zones. And so in order to sort of get this individual addressing in separate zones, we actually have 3 separate beams in free space that address those separate zones. And so we're able to independently control each of those beams, and we can do parallel operations. So moving up a little bit, so walking through some of these sort of actual hardware components in the system of a trapped ion quantum computer. So just to sort of give you a bit of a sense of what this looks like. So of course, at the center of the system, we've got the ions in our trap. And then those are, so that the ions are held in a vacuum system at ultra high vacuum. This is important because if you've got, background gas, right, or sort of other things floating around in your system, right, you can have, other particles come flying through and, like knock an ion out of the trap, or create a molecule, or just otherwise, or, fly by and just generally disturb your quantum system and incur errors. So we need to have an ultra high vacuum system that makes sure that background gas is really, really low. And the only things in the trap are the ions, and there's nothing around to sort of disturb them. We also use cryogens to cool the trap. An interesting note, so this is not, cryogens, having a cryostat to cool the trap is not actually necessary strictly for ion trapping. In grad school, I did room temperature ion trapping, right? Our actual cooling of the ions is done with lasers. However, cooling the trap down using cryogens to, what are we at? 40 Kelvin, I think. So by cooling us down, that just, it's sort of useful for engineering reasons. It makes the system a lot more stable. It helps make the vacuum at the ions a lot lower. So it's more of a sort of a stability helper rather than something that is strictly necessary to do trapping at all. And then, of course, we've got magnetic conditioning around the trap. So if you've seen those magnetic coils, this allows us to better stabilize the magnetic field of the ions, which they are a little bit sensitive to. And then when we do readout, so we have, so we then, in order to actually control these ions, of course, we've got laser signals that we use to do that. So we've got laser sources that produce laser beams that go through signal conditioning and then through beam delivery in order to add whatever sidebands we need, turn them on and off, all those controls that we need to then go to the ions and perform quantum gates. And then for measurement, of course, which generate, as you hopefully recall, generate photons for bright or one state qubits and don't for dark state qubits. We have to collect those photons and measure and count them in order to see the results of our operation. So we've got measurement optics that collect those photons and count them for us. And then, of course, we've got a ton of control electronics that provide the RF and DC signals for our trap electrodes. And then also for all of the optomechanics and optoelectronics in the signal conditioning and the beam delivery that provide all of our laser signals. And then just to sort of briefly go over some of the technology that goes into this. So we have, of course, the ion trap die itself, which again, fabricated by Honeywell. And then with this sort of custom tailored process. We've got cryogenics and vacuum to give us a really stable system in a vacuum chamber with high optical access. And then we have, of course, all the technology that goes into our optical imaging and detection to resolve individual ions with really high fidelity, all the lasers and optics to generate laser pulses, timing, the frequency control of that and deliver to the ions. And then all those control electronics to turn everything on and off, provide really precise timing and precise trap voltages. Marlo, I keep seeing you pop up on video. Are there questions that are coming up?
Yeah, there are many very intrigued questions, and this is very exciting part. We are running a bit out of time. I hope there will be enough opportunity for the questions, but I also want to keep you talking because this is very interesting. So please go through quickly to the best ones, and then we will do some rapid fire questions.
Okay, that sounds good. Okay, so for the software folks in the audience, I will quickly go through our software stack. I work a lot with this on sort of the ion side of things. But as we go down our stack, we have increasing real-time requirements, right? We need really tightly timed controls to perform ion operations. As you go up the stack, you get increasing abstraction from the hardware. At the top, we've got the client layer where basically customers can submit jobs. There's then an access layer, which requires some cloud services to distribute those jobs. There's then a tasking and operations layer where we've got quantum operators that actually operate our commercial systems, and then also have compiler algorithms that sort of take customer jobs and compile them into our native operations, figure out what transport operations need to happen, that sort of thing. And then, of course, at the bottom is our actual real-time execution. So we've got FPGAs that generate very precisely timed signals in real time, and monitoring of various hardware to make sure that our system is still really stable and working well, and all the real-time controls that we need. Okay, a couple features of the Quantinuum 8 series model. So our model H1, we've got two systems that are currently available. We recently released or updated our H1 system, one of our H1 systems, to have 20 physical qubits. That's a big step for us. With very exciting, mentioned the long coherence times. Our coherence times are above 3 seconds. We've measured our quantum volume now to be 4096. Quantum volume is a benchmarking measure that IBM came up with that basically sort of asks the question, a theorist could explain this a lot better. My sort of very hand-wavy experimentalist understanding is it basically asks how many qubits can you usefully, really fully use and fully entangle before you start just running out with sort of the gates that you need in order to do something interesting before your decoherence causes you to just sort of decay off into gobbledygook. And that's generally expressed as 2 to the number of ions, or the number of qubits that you can do that with. So we've now demonstrated this for 2 to the 12, which is also pretty exciting. And our fidelity, our sort of limiting fidelities typically are in the upper 2 nines. And again, sort of features that are particularly handy that we have on the Quantinuum system are we have this all-to-all connectivity, as I mentioned, because you can bring any pair of qubits together and do a gate with them. You don't have to do all these logical swap gates for qubits that start out far apart. We have arbitrary angle single qubit gates, which does allow us to sort of do more optimal operations, because you can, if you're limited to pi/2 rotations, in order to do the single qubit unitary that you want, you might have to do more of those operations, whereas we can do it in a lot fewer and sort of get a bunch of optimization from that. And then finally, as I mentioned earlier, we also have basically mid-circuit measurement and reuse, and the ability to then condition later operations on the results of that measurement. And that's especially useful for stuff like quantum error correction, which is, of course, something that we are really going to need moving forward to get really large quantum computers with sort of sufficiently high fidelities to do interesting stuff. Okay, so another thing I'll briefly highlight is our just some stats. So to my knowledge, we're actually the only commercial quantum processor that's demonstrated real-time quantum error correction. So that means in the same circuit, without having to like break out of the circuit, being able to measure one qubit and then use the result of that measurement to correct an error, and then continue on with the circuit, rather than doing sort of a correction scheme where you sort of have to do the whole circuit, measure at the end, and then you can do things like figure out like, oh, you know, based on the result from this qubit, that means I know that such and such error happened, and therefore I have to like throw out the results from the shot because I know an error happened. But I see on this other shot, based on the output of this qubit, I know that like there weren't any errors, and so I'm going to keep the result of that shot. We don't have to do that. We can just correct errors on the fly, which again, pretty exciting. And then our fidelities. So our single qubit gate fidelity is at 4 nines. Our 2 qubit gate fidelity is 99.7. And our state prep and measurement fidelity is at 99.6. These are some really, really nice error rates. And we're, again, very proud of all the engineering that goes into this. So things, some recent advances, I've got, you know, we're doing, I'm going to cover 2 things. We're doing a lot more than this, of course, but just to give you a sense of sort of things that people are working on. So one is when you are doing measurement, especially doing mid-circuit measurement, you need to be very sure to not disturb sort of the states of the other qubits in the system. You want to measure just one qubit. But of course, there's sort of a few ways that can go wrong if you've got, you know, a qubit elsewhere in the trap that sees either one of the measurement photons or sees a photon that is generated by the qubit being measured. That will of course, you know, destroy its quantum information, and that's a big error. So we want to prevent that. There's a bunch of ways that people have done this with ions. You can just transport the ions to separate locations if they're far enough apart. You're like the probability that another qubit over here that you don't want to measure is going to see one of those measurement photons is really, really low. So, you know, if you just move them far enough apart, that'll work pretty well. You can also do things like map the qubit information to a different ion species. So you would co-trap your qubit with a different ion species, and then you can do some gate between your qubit and your spectator ion to move the quantum information to your spectator ion, and then you measure the spectator ion. And because the spectator ion is a different species, that laser light is not resonant with the other qubits in the system, and so they are not affected by it, and so you can do that measurement on that spectator ion instead. You can also do things like hide qubit states and other metastable levels of the electronic structure of your atom. So you sort of hide all your other qubits into some other metastable state. You measure the qubit that you want to measure, and then you can unhide the other qubits back. And then what we've been doing is, in addition to having sort of our qubits physically separate, we're also now doing something new called micromotion hiding. So a bunch of slides ago, if you remember, if our ion is not on the RF null, right, it experiences micromotion, and so it's moving around a little bit. And so what that means is that if any pulses that it sees are going to be Doppler shifted, meaning the frequency will be a higher frequency or a lower frequency than the frequency generated in the rest frame of your laser. So because it's moving, it doesn't, the ion that we're measuring, right, is sitting at the RF null. So the resonant measurement beam that comes in, it responds to, it generates its photon or not, it's measured, awesome. But for the hidden ion, which is now off the RF null and therefore jiggling around, this resonant beam is going to not look resonant. It is going to look off resonant from that measurement transition. And so it is not measured. And so combining this with some small separation between them, we're able to get sort of even better measurement fidelity and not getting crosstalk onto other ions that we're not trying to measure. Another bit of progress that we're doing is we've demonstrated some junction transport. So on our H1 system, right, as you've seen, like that geometry is very linear. You're moving ions just back and forth in sort of in one dimension. And that works fine for a few ions, but as you go up to more and more ions, that sorting is going to get very, very slow. And so you want some sort of grid structure to allow you to more quickly get ions from point A to point B. So you can think of sort of like a street thing. So we have demonstrated junction transport. If this thing will let me, where's the little, let's have a little video. Okay, the play button is not coming up. I'm not sure why. Sorry. Anyways, so we can. I'm sorry, this is not playing. I'm not sure why, but this ion, we can move it into the center of this junction and move it onto sort of into any of the arms of the junction with pretty low heating rates. We've got a publication that was, or a preprint that was recently posted on the archives that you're welcome to read about that talks about this in detail, but we demonstrated this with, I believe, both single ions and then also with co-trapped barium and ytterbium crystals. Okay, and then very briefly, over the past few years, we've consistently demonstrated increasing quantum volume. So our systems keep getting better and better, which is very exciting, and we're very excited to keep pushing this number up, getting our fidelities better and better, larger systems. And then finally, there's of course the question of where do we go from here? As I mentioned, our Model H1 has a very linear architecture, and we need to move to arrangements that allow sort of faster sorting as we get more and more qubits, and then integrate more and more technology. So our next commercial system that should launch this year, the Model H2, is going to feature a racetrack geometry. So we aren't limited to just back and forth. We can actually go around, and that makes sorting a little faster. And then as we go to H3 and beyond, we're going to start using these grid layouts in order, grids like a city street, which should make it faster to do ion sorting, to get our qubits together, to do 2 qubit gates. And then as we move up further and further from there, we'll start needing to do things like use integrated optics to manage the number of laser beams that we'll need in order to perform all these gates and control all these ions. Okay, so finally, I wanted to super briefly touch on sort of the skills and people that we need in the ion trap quantum computing industry. So obviously this is sort of shaped by, my own experiences working at Quantinuum. But this, I think, should be pretty relevant to the industry as a whole. Types of people we need, obviously atomic physicists like me, optics folks, electrical engineers, mechanical engineers, test and lab engineers, software engineers, theoretical physicists, and systems engineers. And then skills of particular interest in the near future would be things like integrated photonics, being able to work with components in cryogenic and UHV environments. So that'll be as we scale up our system, we need to take the control components, scale them down, and sort of get them closer to the trap. Optomechanics for optics folks in particular, FPGA, RF, and DAC expertise for the electrical engineers, skills around trap design and microfabrication, and particularly for the theorists, quantum algorithm skills. So these are, this is not, you need to have all these skills, these are individual skills that are sort of particular interest, I think, for most folks in the ion trap quantum computing industry. And then skills that I think everyone in the industry should probably try and cultivate. Basic quantum literacy. A lot of particularly the engineers, the non-physicists that we hire, like they learn a lot on the job about sort of basic quantum physics, and that works pretty well. But the folks who do come in with a little more quantum literacy, it makes them a lot more capable a lot sooner, and is just generally very helpful to sort of cultivate that for yourself. And then the other thing is, as actually CELIA mentioned, this is a very interdisciplinary field. We've got a lot of folks from very different backgrounds working together to solve really hard problems. So people who work well with others, who have good teamwork skills, who are very solution-oriented people, who are good at solving problems, who are good at troubleshooting. Those are the kinds of people that that really flourish in this field. And so those are also skills that that anyone wanting to go into this field should work really hard to develop in themselves. Okay, finally, I'm going to end with the obligatory promotion that Quantinuum is hiring. We've got a link here if you want to look into that, and a QR code as well. And then also we do have some programs that provide access to the H1 system for researchers and particularly academics. So Oak Ridge National Lab has a quantum computing user program that helps academics and other researchers get access to our system. And then there's also this Azure Quantum Credits program from Microsoft as well. And with that, I will stop and ask for questions.
Wonderful. Thank you very much for this fantastic presentation, Caroline. The visualizations and animations at the end were extremely insightful. Vashnavi says, this is one of the best sessions we have had. Other people said, oh yeah, please go on, even if we run out of time. So thank you very much. And there are many questions. I will try to ask them to you rapidly and hear the questions for you from the answers from you and keep on going. Let's start at the start. Why do you use ytterbium and not others? And why this specific isotope? Have you tried other isotopes?
Yes. So why ytterbium? So ytterbium, basically every sort of specific species and isotope that you'd want to use can have different sort of upsides and downsides. So there's a lot that goes into the sort of species decision. And I will not really even be able to give a super in-depth coverage of this, but I can at least sort of give you a sense of what goes into that decision. So ytterbium-171 is nice because it has what we call a clock state. So if you remember that diagram from a zillion slides ago, where we had that hyperfine splitting of only 12.6 gigahertz between the 0 and 1 state, and it's with a spin 1/2 qubit. You do a bunch of math, and what comes out is to first order that pair of states is insensitive to magnetic fields. Of course, that's only to first order. There's that does unfortunately mean that eventually, if you're trying to do higher and higher fidelity operations, you do actually eventually start noticing the effect of local magnetic fields on your qubit. And actually, funny story, in our labs, because of the really high fidelity operations that we try and do, if you do something like move a steel ladder around the lab near the optics table, you will actually see your qubit frequency change. We also see our qubit frequencies change with solar activity because that has sort of small effects on the magnetic field of the Earth, which is sort of the background magnetic field that we're doing all of this in. And in fact, one of my coworkers put together a poster for a conference recently, basically showing how we could see our qubit frequency changing sort of in concert with like solar activity and background, or like magnetic fields tracking that is done at I forget which laboratory, but up in Boulder, so very close by. And you can sort of see that like our qubit frequencies track with solar activity. So it's just sort of mind-blowing stuff. But other qubits that don't have that clock state, like ytterbium-171, are even more sensitive to that. We're sort of, just already like into the margins of how, how high fidelity our qubits can be. Other nice things about it. Let's see. So another thing that people take into account is basically the frequencies of the lasers necessary to do the operations in question. Ytterbium-171 is not super ideal because the main operations that you need to do, like for those stimulated Raman transitions and so on, require lasers at 369 nanometers, which is in the near UV. If you have a qubit that is in that has all of its transitions in the visible range, right? So colors you can see from red to purple, that is a lot easier in terms of sort of the technology available, there's a lot more lasers available. There's a lot more options for optics. Your fiber optics, there's some really good fiber optics for visible light, stuff like that. So Ytterbium-171, unfortunately, because it's in the near UV, so it's not like super duper bad, but it does sort of mean that it's a lot harder to do things like put that relevant light through fiber optics, because there aren't really good materials yet, at least for fiber optics that can carry UV without sort of a lot of power loss in the process. So that's another thing that goes into it. There is actually a qubit that looks a lot like Ytterbium-171 in terms of having that nice clock state qubit, but is in the visible, in terms of the, like its transitions are in the visible range. That is barium-133. Unfortunately, barium-133 is not a stable isotope, and it decays with a half-life, like it's long enough that you can use it, but you do have sort of this additional overhead of like, you know, my qubits are radioactive, so you sort of have to manage, you know, how do I deal with the fact that this substance is radioactive? You know, your sources that you put in these vacuum chambers are only going to last so long before you have to break vacuum and replace them. And of course, breaking vacuum is a huge deal. Stuff like that. There's also, so Ytterbium-171 is a clock qubit, right? It's got that very close splitting. You can also do quantum computing with what are called optical qubits, where the states that you pick as your 0 and 1 have a separation that is optical, meaning it's a frequency that is sort of in the laser regime. So, you know, 700 nanometers or something. You can definitely do quantum computing with those, but those also have some downsides, like being more sensitive to magnetic fields. Yeah, there's also other considerations include things like, you know, how easy is it to get sources, to get isotopically purified sources, how and then be able to you know, to get those atoms into your trap with loading from an oven. How the mass of the ion also has implications for sort of how, like, various aspects of the trapping potential itself. Lighter ions tend to be a little bit easier to deal with. There's also, if you want to co-trap different species to do stuff like the sympathetic cooling that we do, you generally want those species to be closer in mass. If they've got really different masses, that also sort of makes it harder to get a really good trapping potential with sort of the parameters that you'd want. So even if, so that can also influence things, because if you've got, you know, oh, this is the best ion ever, but, you know, every other, or like there aren't really any other decent candidates for sympathetic cooling ions anywhere near that mass, that ends up making it a lot harder. So that's a definitely incomplete list of factors that go into species selection.
Yes, amazing. And thank you so much for the anecdotes with the steel ladder, the solar activity. Wow. And you answered several other questions also about the magnetic stability and some other very good questions. There are more questions about from one atom to many, or ion. How can you make sure that you just have one ion in your system, or several? And so having the precise number, and is there any limitation to the number of qubits eventually?
Yes. So, I mean, the limitation is honestly going to be about engineering. You know, how well can you, for, you know, specific to our architecture, you know, do you have enough room in your trap to have all these qubits and then still sort of have the necessary room to like shuffle them around each other, and then and have enough, you know, like some grid architecture or other type things that allow you to move the ions around, or sort of sort them fast enough that you aren't just waiting forever to do a single 2-qubit gate, because, you know, the qubits started at opposite ends of the trap. So yeah, speed of sorting, and this is sort of QCCD specific. In the general case, with the large traps, you do actually, where you've got a single potential wall with a really long chain, you do actually start running into an issue where the normal modes of motion of a chain with, let's say, 200 ions, you actually, because there are so many normal modes, the number of normal modes is the same as the number of ions in the trap. Because there are so many, you start ending up getting situations where some ions will participate more in certain modes than others. And in fact, some ions might not really participate in a certain mode at all, where, if that mode is activated, it's like barely does anything. And so it's very hard to couple to that mode. And so if you then have an ion that couples well to modes A, B, and C, but not well to D, E, and F, and then you've got another ion that couples well to modes D, E, and F, but really poorly to A, B, and C, it's really hard to do a direct gate between those two because they don't really have modes in common that you can that they both couple to really strongly and therefore can drive that gate. So you start having sort of connections that start dropping out. And so then you'll sort of need to manage that in other ways. Other limitations. So as you scale up the number of qubits, you also have to scale up the number of laser controls, as well as the number of electrodes on your trap are going to get larger and larger. And so with the electrodes on the trap, of course, you then have to start worrying about like just the massive number of wires necessary to control all of those electrodes. So you want ways to reduce that load a little bit with the number of sort of control laser beams that you need. If you've got just massive numbers of ions and everyone needs an individual beam, or like massive numbers of zones and all of them need an individual control beam, you start getting just massive numbers of free space beams. And in free space, that sort of management of all those optics, the aligning that you have to do, the number of optics involved, and like how much space on a table that takes up to have all those optical beam lines, that can blow up really fast. The solution to that is, as I mentioned earlier, integrated photonics. So that means being able to generate, but basically being able to rather than have those beams go through free space and then like out in the world and then go through the window into a vacuum chamber, you instead ideally would be able to do things like do all of your sort of or like do a bunch of beam generation and then put those into fibers that then are routed inside the vacuum chamber and then actually come out like on the trap somehow. So somehow getting a lot of your optical controls into a space where they're able to sort of be in be in components rather than in free space, and then getting them to the trap in much more efficient ways. Okay, so that sort of challenges with scaling. Sorry, I think there was another component to the question. Can you remind me what it was?
You already gave great insight in many parts and even some other questions. So that is great. Juliana from Italy points out the high quantum volume. Does that translate in less iterations of variational quantum algorithms for QML?
Oh, I have no idea. You should ask a theorist. Sorry.
Or generally, there are many questions about the comparison with what Quantinuum is doing, other TrappedIon companies, and also the direct comparison with neutral atoms.
Yeah. So I'm primarily an expert in the things that I've done. So I can't necessarily speak completely accurately to things that specific other companies are doing, or things that sort of other qubits are doing. As far as like us versus neutral atoms, and again, I did like a little bit of undergrad research with neutral atoms. But so for those who are a little less familiar, so in terms of sort of like physics fields, So I'm an atomic physicist. The field is sometimes referred to as AMO physics, where AMO stands for atomic, molecular, and optical physics. And that's basically because the work that we do is stuff with, like, individual or very few atoms, and or sometimes very small molecules that we poke with lasers to make them do interesting things. That's the AMO field in a nutshell. So trapped ions is sort of a subfield of that, or a subfield of the subfield of AMO physics within physics. Neutral atoms are another subfield. So we're, sort of like, we're very closely related fields in that we've got a lot of techniques in common. And in fact, at Quantinuum, we hire a ton of neutral atoms folks who then, are able to transition to the particulars of ions pretty easily because they already have a ton of background in sort of the general atomic physics knowledge necessary, the lasers, optical techniques, stuff like that. So in terms of if you walk into a neutral atom lab or an ion trapping lab, physically they look pretty similar. You generally have an optics table covered with optics. You've got ultra high vacuum chamber somewhere in there. You've got a lot of laser beams that are going into that chamber. You've got a bunch of control electronics that send very tightly controlled signals to make stuff happen. And you've got some poor AMO grad student sitting at a computer, running various operations and hopefully doing something new that they can write a thesis about. However, the sort of the differences specifically for quantum computing. So trapped ions obviously are charged particles, so that the way that we can hold on to them is very different than you would with a neutral atom. So we've gone over ion traps. With neutral atoms, they're not charged. The way that you have to hold them is with lasers, and it's usually with why is this name escaping me? It's usually sort of they'll generate like a lattice of laser beams that are sort of intersecting, and then you can hold on to neutral atoms, I think, at the intersections. And I'm probably going to screw this up at least a little bit, but the basic idea is that you have that optical lattice. You can hold a neutral atom there. You store, I think in most cases, you store the quantum information, as I said a whole bunch of slides ago, in the highly excited Rydberg states. So those are like sort of, I think of them as being way up in the stratosphere of the atom in terms of the internal electronic structure. And then I forget how many two gates. I should probably know that. But that's sort of the big difference between them, is the way that you're holding them, and then as a result, the way that you're doing gates. Right? There's no trapping potential in neutral atoms, therefore there's no shared modes of motion. So the way that they do 2 qubit gates is totally different. So yeah, the particulars are very different, but a lot of the sort of physics skills and a lot of the actually a lot of the sort of engineering support skills as well are very, very similar.
Thank you very much. And we would actually love you to have, we would actually love to have you for an additional Q&A session. You're such an expert with so many answers and insights for everyone.
Yeah, I don't have a hard stop. So if there are more questions, I can take them.
One important thing that you pointed out were the career opportunities, and also that people from many different backgrounds join Quantinuum and generally the trapped ion field. As long as you have some quantum literacy is very important, and teamwork and troubleshooting. Why did you choose yourself to go into quantum computing?
Well, if I have to dial back a little bit. So I actually first learned about quantum computing as a thing in middle school or early high school. Like I'd sort of always been, interested in particularly the physics articles in sort of like the science section of the newspaper. Like I remember in 5th grade, there was like this big 2-page spread in the science section of the New York Times about string theory And I was like, I don't understand any of this, but it's super cool. And so like, I'd sort of, I think like looking back, I'd sort of always been drawn to a lot of the physicsy kinds of things. And also I was really interested in computers. I liked working with them. I like playing video games on them. I think going to college, I already knew that I was pretty interested in both physics and computing, and reading some articles about quantum computation. That's like, oh, this is clearly where computation and computing is going. Like, this is the next, this seemed to me to be like, this is the next big computing technology. And that was really interesting to me. And then when I got to college, I ended up taking a pretty cool seminar about quantum computing. And I told myself, like, oh, I'm not decided about my major. I'm gonna like take the intro classes and then decide. And by the end of like even that first semester with that quantum computing seminar, I was like, oh yeah, this is what I want to do. So I double majored in physics and computer science, because quantum computing, obviously I need to study quantum and computing, right? That at least that was my logic as a college freshman, which isn't necessarily quite the correct logic, but it worked out. And then I ended up going to grad school, and with my grad school applications, I was very focused on quantum computing specifically. And so I ended up doing ion trap quantum computing at the University of Maryland. And it was the specific group that I was in ended up being very quantum computing focused, which was just, to some extent, there was a certain amount of luck that went into that. But it was exactly what I wanted to be doing. And that, everything sort of followed from there. I graduated, I got hired at Quantinuum, and I'm still doing ion trap quantum computing, and it's pretty great.
And we all hope you will keep doing it and push the field forward.
Yes.
Thank you so much, Caroline. We will
very
conclude
welcome.
the session now. There are some more questions. I will relay them to you. I will give some feedback. Juliana says, thank you very much for the outstanding lecture and the accurate answers to our questions. Kudos for your energy. Others say, thank you for the great talk. One of the most interesting presentations, plus the animations were very helpful in understanding many things. Thank you very much. And I will briefly take over the screen sharing to show tomorrow's session, because we have another very exciting session coming up. So this was today, the quantum ecosystem needs you, which Caroline also emphasized, especially for the trapped ion quantum computing field. And tomorrow we will go beyond quantum computing. We will talk about how to couple these quantum computers or devices in a quantum internet, presented by Pranay Narang, CEO and co-founder of Aliro Quantum and a professor at Harvard University. And then we will move towards quantum biotech and talk about living quantum sensors at the nanoscale. Did you know, for example, that birds use quantum to navigate? Looking forward very much to seeing you tomorrow again. Thank you again, Caroline, for this fantastic talk and giving us so much insight into trapped ion quantum computing. And we hope this is only the start for everyone to learn about this. And tomorrow we will keep learning about other topics in quantum, and the same holds for the next 2 weeks. And then the hackathon. So we will all keep learning. It's only the start. Thank you so much all, and see you again tomorrow.
Thank you.